Bismillahirrahmanirrahim. Today we will start with optical activity. Molecule which rotate plane of polarized light is optically active. If this molecule rotates light to the left, then it's called levorotatory, represented by L. And if this molecules in polarimeter rotate the light, the plane polarized light towards right, then it's called dextrorotatory and symbolized by small d. Here you can see the ordinary light which is oriented in all the directions. But when this light passes through a polarizing filter, it is to be transformed into plane polarized light. Now, this plane polarized light, when passes through a solution of chiral compound or the molecules of the chiral compounds, then after passing from this medium, the light bends, and this bending of plane polarized light gives some specific rotation, optical rotation, which is to be represented by this angle alpha. And if the molecule in the solutions are the molecules in the solutions, they are dextrorotatory, then this angle would be toward the right side. And if the molecules in this solution are levorotatory, then the angle would be the on opposite side. The basic condition for an optically active molecule or a compounds are the presence of central carbon atom in the molecule, and this central carbon atom would be attached to 4 different atoms or groups. The second condition, which is very important, in such molecules, there would be no element of symmetry. As you know, there are different kinds of the element of symmetry. For example, plane of symmetry, center of symmetry, alternating axis of symmetry, etc., etc. In the chiral molecule or the molecule containing chiral carbon, they would be lack of any element of symmetry. Here see example 1 and example 2 of the molecules which are optically active. In the first example, you see the carbon here, which is bonded to 4 different atoms. That's our hydrogen, chlorine, fluorine, bromine. So this carbon is chiral carbon, also called asymmetric carbon. Now in this molecule, there is no symmetry element. There is no plane of symmetry. Similarly, come here in the second example, you can see the carbon is asymmetric or chiral carbon attaching to different atoms and groups. So all 4 groups are the atoms. They are different. So structure 1 and 2, they are both optically active. In order to show symmetry, we shall take the example of CH4. Here you can see the carbon which is bonded to similar hydrogen atoms. So the molecule is symmetric molecule, and the carbon is not asymmetric carbon, or this carbon is not chiral carbon, because this molecule has planes of symmetry. For example, you can cut this molecule from this hydrogen to carbon to this hydrogen. You can see here. And after cutting this molecule, you will get two halves, and the two parts or the two halves will be equal to each other. The mirror images of these two halves would be superimposable on each other. Similarly, you can cut this molecule from here to here, and then after cutting, you will get the same two halves. Similarly, if you cut from here, you will get the same two halves. If you cut from here, you will get the same two halves of this molecule. So this molecule consists of the plane of symmetry. It is having plane of symmetry. You can see 1, 2, 3, 4. So due to this, the presence of the planes of symmetry, the molecule as a whole is optically inactive. Come here in this example. Here the carbon has two same atoms, that's our hydrogen, but this group, OH group, and this atom, they are different. But still, this molecule contain plane of symmetry. You can see here, this is the plane of symmetry. You can cut this molecule from fluorine to carbon to O to H equally. And after bisecting this molecule, you would see the two mirror images which are superimposable to each other. They would be equal with mirror images to each other. So the molecule is having plane of symmetry. Hence, molecule is optically inactive. See here, this carbon, this contain 4 different atoms or groups here. So this carbon, which is bonded to hydrogen, chlorine, methyl group, and the OH group. So the 4 bonds of the carbon, they are having different atoms and groups. The carbon in the center would be chiral carbon or asymmetric carbon. So you can cut this molecule from here to here. You will see the two halves would not be equal to each other. If you cut from here to here, you will see the two halves after cutting would not be equal to each other. If you cut from here to here, then the two halves would not be equal. Similarly, if you cut from here to here, then the two halves, after bisecting this molecule or cutting this molecule, would not be equal, would not be mirror images to each other. Hence, this molecule is lack of plane of symmetry, or any other kind of the symmetry element is not present in this molecule. Hence, on these bases, we called this molecule is optically active molecule. The other examples to show the symmetry or dissymmetry. So here you can see the carbon atom, which is attached to four different atoms and groups. You can cut this molecule from here to here, from here to here. So if you will cut from here to here, from here to here, from fluorine to carbon to chlorine, or from H to C to OH, you will see the two parts you are getting due to these operations would not be equal to each other. They would be non-superimposable to each other. So the molecule is having chiral carbon and the molecule as a whole is optically active. Come here, see this molecule having two hydrogens. So having one plane of symmetry as explained earlier. So this molecule, if you cut from here to here, you will get the similar halves that would be mirror images to each other, and they would be superimposable to each other. So this molecule is optically inactive. Now we come to the mirror images of optical active molecule. Here you can see one example, the carbon having different groups. So if we place the mirror in between, then on the other side, the reflection of this molecule would be this. So this structure number 2 is actually the reflection of this structure number 1. Or we can say 1 is mirror image of 2 or reflection of 2. So such type of the condition would always be present in optically active compounds. So 1 and 2 are also called enantiomers, and they are non-superimposable to each other. Just like our hands, that our hands are also non-superimposable to each other. So this is another necessary condition regarding the mirror images of an optical active compound, that they always be non-superimposable to each other. This situation is explained here if this structure number 2 is drawn with red, and if this drawn with black sketch, then if we take this structure number 2 and put this structure number 2 upon this structure number 1, we will get the situation like this. Here you can see the carbon of structure number 1 represented by black, and the carbon of structure number 2 is represented by the red. So here you can see The COOH or the carboxylic group of this structure 2 is coming just upon CH3 of structure number 1. Similarly, the CH3 of this structure is coming upon the COOH of this structure. You can see here. So this kind of the situation called superimposability as non-superimposability. This kind of the situation called non-superimposability. So this non-superimposability is present between the mirror images. So as a whole, the molecule of the lactic acid, which is present here, would be optically active. Another very important question is that how the optical activity is caused, mean cause of optical activity. So in order to explain this question, we can say that light travels in form of electromagnetic waves, and a chiral molecule has bonds having electrons in motion, so emitting electromagnetic waves. When plane polarized light passes through a chiral molecule, the electromagnetic waves of molecule and light interact with each other, and plane of polarized light bends due to repulsion on one side at a certain angle, showing optical rotation or optical activity. A molecule which is not chiral, that which possess plane of symmetry, the optical rotation of one half of molecule is opposite to the other half of the molecule. Therefore, two effects cancel each other, showing no optical activity or optical rotation. As chiral molecule is not symmetrical and optical rotation is nowhere counterbalanced by two halves inside the molecule, and as a result, a net optical rotation of plane polarized light occurs at certain angle. In order to show the cause of the optical activity in the chiral molecule, here we can depict by this sketch. For example, this is plane polarized light coming to the molecules which are chiral in nature. We're taking the example here. This is the chiral carbon having the CH3 group on this side and carboxylic group on this side. Here, the light is traveling. This is the plane polarized light, and you can see coming like this. Here, the environment of this side of the molecule is different from the electronic environment of this side of the molecule. This is the CH3 molecule having the 2 electron in this bond, 2 electron in this bond, 2 electron in this bond, 2 electron in this bond. So there are total 8 electrons on this side. And if you count the number of the electrons in the bonds in this side, you will see the total number of 18 electrons are present in this side of the chiral molecule. So they are producing electromagnetic waves. These electrons, they are producing electromagnetic waves. Now, when this plane polarized light with electromagnetic waves would come, it will interact on both sides of this molecule. This side of the molecule having more number of electron as compared to this side. So the plane polarized light will face more repulsion on this side and the light would bend. This bending of the light then after coming to the analyzer would show the optical rotation. And similarly, you can see the examples of the non-optically active compound in similar way to see the environments of the electron on both sides of the carbon. So this is all about some lecture regarding optical activity.